Hello and welcome back to Calculus 1. We are going to start the first of the three major parts of calculus, and that one is called limits. Now, limits are going to be the base for us to describe derivatives, to describe integrals, but in reality was the last thing that was defined, which is very interesting. So Newton starts off calculus in 1666 with the notion of the derivative, which is applied to physics and so on. Leibniz does it at the same time, but applies it to economics and money. And calculus was developed by these two guys independently, which means that the time was just right for all of that to happen. There were some early indications at that time about integration as well. Integration was well developed in 1700s already. The definition of the limit that you guys are going to see at the end of this chapter was defined in 1850. So it took so long, right, to actually get these limits mathematically sound and concrete. So we learn to work with limits, we learn to compute limits, we learn what they are, but the actual definition and all that stuff is at the end, so we'll deal with that, I think, Thursday. If not Thursday, then Monday next week, but we'll deal with that very soon. The question is, what are limits? And the very basic answer, the one that you would offer to your, friend, you go out, right, Friday, Saturday night, casual talk at the, wherever you are, limits come up, right? And then your friend goes, what is a limit? And you say, okay, here you go. This is the cheapest possible way to explain a limit. Limit is a fancy way to calculate y value of a function. That's the cheapest thing that you can say about the limit. Limit is and the word fancy is very important. So limit is a fancy way to calculate the value, the y value of the function.
It should be f of x.
Okay, calculate y value of f of x, sure. You can also spell function, you can say f of x, whatever makes you happy. Remember, it's all about your happiness and zen. Right. So let's say you have function f of x equals x squared minus 1. And you would like to calculate f of 3. Well, that's going to be 3 squared minus 1 equals 8. And you're done. Yay for pre-calc, right? Algebra. Plug in the value and you are done. So there is nothing special, right? This is it. You computed this and you're done. So I'm going to call this pre-calc. Now, calc. What is the limit of x squared minus 1 as x approaches 3? And the answer is going to be 8. Right? But now you're going to say, what does this even mean? X approaches 3. Well, remember what we said yesterday. Calculus is study of change.
Mathematics of change.
Yes, mathematics of change. So, as you are going somewhere, aren't you changing your position? Yeah, you're changing your position. When you are parked at the red light, I stopped at the red light because it's red, I hope you do that. You have to change your velocity, your speed, from 0 to whatever you are driving at in order to move. Because if there is no velocity, you are not changing position. Do you see kind of double change there? You gotta change the velocity from 0, because your speedometer is reading 0 when you are at the red light, right? So if you never push your gas pedal, are you ever gonna get anywhere? No, right? Your speed will never go up. And the thing that changes your position is the speed. So in order for you to change the position, you first have to change the velocity with the speed. Wow, that's cool, right? So you understand now that motion, right, the position of where you are, is related to how fast you're going. It's related to concepts that we study in calculus. So now when I say x approaches 3, I literally mean x approaches 3. X is moving on the x-axis. X taking all of the values, moving towards 3. And you can approach 3 from two different sides. You can approach it from the side, from left or from right, right? From number 2 or from number 4.
Direction is the negative.
Yes, so direction is the... So now, if I draw my x minus 1 parabola, and say this is negative 1, and let's say this is where 3 is. This 3, looking at the pre-calculus, this 3 will give us a value of 8, which is the answer we're looking for. So if you are dealing with your pre-calculus concept, all you need to do is to draw the vertical line until you cut the function, and then you cut across to y, and wherever it crosses it, that's the y answer. So what you see in this drawing right now is what the pre-calculus does. Now, what I'm going to do is what I call Romeo and Juliet approach. All right? We're going to have approach 3 from the left using this red arrow. Now I want you literally to walk on this line in your head. And as you are this x that's walking on the line towards 3, you are technically going up. Do we understand that idea? As you are moving to the right, over there, as you are moving to the right, you are technically moving up the curve. Are we all cool on that? Which translates in the motion moving up on the y-axis. So these red arrows all work at the same time because it's an image. So think of a value right here, bounces off, it's there. Next value, go here, bounces off there. Next value goes there, bounces off, and so on. So you see that as I am getting closer to 3, the y values climbing towards 8. So that's your Juliet. Right, that's the red stuff. Yes. No. Yeah, we'll deal with that tomorrow. But Romeo, blue, right? Approach from the right, going left. Well, he is going to go down the curve and down the y-axis. And what you see here is that they approach from two sides And as they approach from two sides, they approach here, and their y values approach, and they meet at 8. That make sense?
Yes.
So as it squeezes here, it squeezes there, it squeezes there, and there it is. Now I actually want to do this calculation. This was the graphical understanding of working out the limit. We can do the same thing using a chart of values. What I'm going to do is I'm going to approach 3 from left and right. Red 2.9, 2.99, 2.999. This is Juliet approaching 3 on X value. So you can think of it as, if you think about 3 being $3, then you are 10 cents away, then you are 1 cent away, and then you are 1/10 of a cent away, right? So each one of these numbers is closer to 3. On the Romeo side, we have 3.1, 3.01, 3.001, as Romeo is getting ever closer to 3. So now, we're going to do calculation. So we're going to plug all of these numbers into our function and compute their y values. So we are going to use x squared minus 1, and I'm just going to plug all of that stuff in my calculator here. So do we all have 7.41 for the first?
Which one?
For 2.9.
I started there. Hold on.
What do you mean you haven't started there?
I started with 3.001 squared.
All right. Now we do the
41.
next one. At 7.94, and then 7.994. Do we see 7.4, 7.9, 7.99? Where are these numbers going?
Towards 8.
Towards 8. So we see, as we calculate y values one by one, that this is pointing towards 8. Now we do the 3.1.
99.
So that's 8.61 all the way at the end. And now this should be falling towards 8. So 3.01. Oh, look at that, 0.06 now. And then finally 8.006. Do we see that it falls into 8? So overall, in black now, if it walks like a duck and quacks like a duck, it's a 8, exactly. If it walks like an 8 and quacks like an 8, it's an 8. So this is the way for us to calculate limits. And you would say that this is absolutely insane. Why would I be calculating, values if I can just plug in number 3, get 8 and be done? Why do limits even exist? It's madness. Well, no. Limits are more advanced and limits have more power than what pre-calculus gives us. And yeah, some limitations and things, we'll see that, but the idea is that, see, the point 3, actually 0.38, doesn't have to be defined on the function. And pre-calculus cannot deal with that at all. If this 0.38 was an open circle on a graph, your pre-calculus calculation would just give no value. There will be nothing there. Now, have we computed a 3 ever when we did limit? No. Now let's explain that word fancy. Remember, I painted a picture of you going out, talking to your friends, limits come up, and right? You were supposed to just say, oh yeah, the limit is just a fancy way to compute y value, nothing special. Why fancy way? Well, plugging in value is the pre-calculus way. Everyone knows that. But see, the trick is that it fails if the point is not defined. Now look what calculus did, what limits did. Limits calculated everywhere except at 3. Right? You can pick any values you want. How many numbers do you have between 2.99 and 2.99? How many numbers do you have? Infinitely many. Okay? So, limits compute infinitely many numbers on the left, infinitely many numbers on the right, and then they say, oh, this is the trend, it's 8. You never computed at 3 with a limit. Never. You never computed 3 directly, because limits open possibility to you to compute also the values that are not present on the graph. And that is something that it's actually very powerful, because you can compute a lot of stuff even if the values are not there. So, believe it or not, that's it. Now we're going to take a look at situations where limits don't exist. We're going to define red and blue arrow and all of that stuff. But I just want to tell you that there is nothing else in terms of trying to figure out a concept. It is literally computing infinitely many values here, leading up to the 3, infinitely many values here, leading up to the 3 from the other side, and if they end up being the same value, that's the limit and that's the answer. On the other hand, if they don't end up being the same value, well, then the limit doesn't exist. And let's take a look at that situation as well. So, for this example, I will use the piecewise step function, let's say taxes, right? Death and taxes. So just taxes, no death. Don't panic. Just taxes. So, I don't know what the brackets are. We can pull up and get it, but who cares now? Let's say if you're making less than 10K, you are paying 10%. If you are making less than, I don't know, 25K, you are paying 15%. I'm just making this up. And then if you are making 25K and above, 20%. I just made all of this up. So this is a percent you pay for taxes, and this is the money you make a year. If there is a closed circle here, there better be open circle there. If it's a closed circle there, better be open circle here, because we know we can't have two closed circles, one on top of the other, because that ruins uniqueness and ruins the function and our day together with it in calculus. So now, I'll call this function t of x as a tax function. So what is the limit as x approaches 9k of the tax function? Well, the answer will be does not exist. Why? Why doesn't it exist? Because the left side and the right side do not agree at the value at 9k. See, when you approach from the left, which is the red approach, the Juliet approach, as Juliet approaches 9k, she always pays 10%. And as Romeo approaches from the right towards 9k, he is always paying 15%. There is no point at which they would be paying the same amount. In a previous example, the common number was 8. They agreed at 8. We say converged to 8, right? So now they diverge. There is no point at which they get to pay the same tax. So in the red case, limit x approaches 9k, and then we put the minus here on top, signifying approach from the left of the tax, is always 10%. And the limit x approaches 9k plus of tx is going to be 15%. So now, these two are not the same, meaning because they're not the same, the overall limit does not exist. So I'll go through this argument one more time. Observe that all of the y values for Juliet, which is red, are all 10%. All of the y values are 10%. So if I plug in 5k, it's 10%. If I plug in 7,036, still 10%. If I use 8,099, still 10%. If I go on the blue side, no matter which number I pick between 9k and 25k, it's always going to be 15% on the y value. You pick 10k, it's 15%. You pick 20k, it's 15%. You pick 9,001, it's still 15%. So all of the values between 9 and 25k are all 15% on y, and all of the values from 0 to 9k are 10% on the value. So in this case, right, you guys have, there's no agreement, right? And we have that the limit does not exist because they did not end up being and the same, like over here, right? 8, 8, and then 8. They all agreed that it's 8. In our case here, they don't agree, right? It's 10%, it's 15%, so overall limit does not exist. So now, we're going to define one-sided limits. And then we'll have this major theorem which helps you solve problems down the line in this class. So approach from the left.
Oh yes, I was reading about this earlier. It's either they can either approach from the left or the right.
Well, it's if it exists, if the function exists, not for all. I'll explain that as well. So approach from the left would be the limit x approaches a minus of f of x. So that's the notation. And the meaning is you are approaching your value from the left. So that's the Juliet, which is what we had in red all the time. Let's say exponential function, and then you have your value over here, whatever, a, and you are approaching from the left. Now, approach from the right.
X has to be less than a, right?
No, just oh, well, yeah.
I've seen something about that in the textbook, but textbook earlier.
Well, you are approaching the value from the right. So your values on the right are this way.
Yes.
So your x is bigger than a in this case. So those are the one-sided limits. When you have this plus and minus on the number, you all see plus and minus where they are?
Of course.
You know when you write x squared, well, instead of x squared, you just now have a to the minus. That's the superscript up there. All right, great. So finally, we are ready for our first major theorem. And this is the theorem that helps you solve problems. So this is the stuff that you are supposed to learn. If limit of f of x as x approaches a minus is the same as the limit of f of x as x approaches a plus is equal to some value, call it L, then limit f of x as x approaches a is equal to L. Otherwise, limit does not exist. We say that that the DNA, right? DNE, no DNA, DNE. What you see here in this theorem is what we have done in the previous two examples. I'm going to go back to our very first example here. Show the picture and the chart at the same time. And when you approach from the left, that's your limit, which was denoted as a minus. You would be writing limit x goes 3 minus for this one. So this is your limit 3 minus. You are approaching from the left. And the blue one is a 3 plus. Now what does it say? If the limit from the left, which in our case was 8, that's your L equals 8, and the limit from the right, which is your, again, L equals 8, if they have the same number, then the overall limit, which is what we have in a problem, the overall limit is that value. Do you see how I am asking up there? X approaches 3, no plus, no minus. That means from both sides at the same time. And the answer is 8. The answer is 8. Answer is 8 because the left limit was equal to the right limit. This is the theorem that actually tells you what the answer is. So, conclusion of the first example. I am restating it now. Because the limit from the left and the limit from the right are both 8, overall limit is 8. Now, the second sentence in that theorem says, otherwise, limit does not exist. Well, if the statement was if the two limits are the same, then the overall limit is the same. Then otherwise means if the two limits are not the same. Well, that's the next example. The red limit was 10, the blue limit was 15. That's not the same, and that's the reason why the limit does not exist in this case. So this is the major idea of the entire lecture. You can also add underneath the sentence, one-sided limits always exist, right? One-sided limits always exist. Now, the two-sided limit, the overall limit, might not exist if these don't have the same value. So this equal sign is important, right? Because it says that the left limit has to have the same value as the right limit. Otherwise, limit does not exist. Bueno? Oh. Yes, so one-sided limits always exist. Two-sided limits, well, depends. If the one-sided limits are the same, then yes. If they're not the same, then no. Now, let's do one more example, and this example is going to be worked out on a piecewise function. So, what's the limit as x approaches 2 of f of x? That's the question. Now, f of x is given as, and we have now the piecewise function. Say over here you have x squared minus 3x for all x's less than 2. And then you have x plus 9 for all x's bigger or equal than 2. Sure, you can graph this. No one cares because we don't need it. The Juliet approach, which is the red one from the left, the limit of f of x as x approaches 2 minus. Which part of the function do I get to look at? The upper one or the lower one? And why? The upper one. Why? We're coming from the left, and that's where the values are smaller than 2. Great. So, we are looking to find the limit, 2 squared minus 3 times 2, which is going to be 4 minus 6, which is negative 2. Blue approach, limit x approaches 2 plus of f of x, which is going to be the bottom one, which is 2 plus 9, and that's 11. Negative 2 is not the same as 11, so limit of f of x as x approaches 2 does not exist. Observe that both of your one-sided limits exist. The red one, right, the approach from the left is negative 2, and the blue one is 11. So both one-sided limits exist. The overall limit does not exist because they do not agree. The red and the blue number are not the same, and that's why the overall limit does not exist. The theorem clearly states only if they are equal, the limit exists and it's L. If they are not equal, Well, that goes in the otherwise part. The limit does not exist. I don't have any kind of ending for this, like the grand finale or whatever, like fireworks. So I just end